lecture we talk about the multiple step method, and we said this method it's super provide accuracy better than a single step, because here we use data from the past. If we have a bank of data from the past or previous data, so this data it's help us to provide a better accuracy or better estimation of the function, better approximation, and also better predicting of the functions of the value yi plus 1. So for example, the difference here, if we use the standard one, we use xi, the point here, after that we compute the slope to predict the value at xi plus 1. But in multiple step, we need multiple step or previous values of xi and yi. For example, -1, -2, -3, -4. How many steps that we need? If we increase the steps, in this case, the accuracy will increase, will enhance. So this method is used to enhance the accuracy, but here we talk about accuracy measurement that we have it before. So if our measurement before is accurate and we use the previous data, so in this case we can enhance the accuracy, and also we can predict, or we can provide a nice predict of the functions. And we studied different methods like non-self starting Huygens method, where we use a two-step predicting, because here we look for data from the past, yi minus 1, and just we modify the form. And we talk about methods, two steps predictor corrector. So in this case, we need two slopes. After that, we average them. Two steps, the slope at xi and slope at xi minus 1. After that, we take the average between them. We can use 4 steps. We call these 4 steps Adams-Moulton predictor corrector. So in this case, we use 4 steps. That means we need 4 slopes at xi, slope at xi minus 1, slope at xi minus 2, and slope at xi minus 3. So we compute the predictor. After that, we update the corrector. How many iteration that we need? It's dependent on the question and the accuracy that we look for. So what we want to focus today is to talk about a finite difference for boundary problems. Why we talk about boundary problems? As we said in the previous lecture, if we talk about this is the root of or any chemical process, and instead to start from one initial condition, for example, at this side, T0, and here, for example, Tn, assume this is the final value, so this is equal 50 degree. So instead of starting from one initial condition, so here we have two conditions, two boundary conditions at different time. So the first condition, we have temperature at point 0 is equal 100 degree, and we have temperature at point n, it's equal 50 degree. What we started before, we start from initial condition x equals 0. All the problems that we studied before, it's equal, for example, 0, and we have y at 0, it's equal, for example, 1. So in the initial value problems, both started at the same point. But here in the boundary value problems, we have two conditions but at different points. So we call these boundary value problems. The best way to solve this one is by using finite difference method. So here, as we said, we have two boundaries, or it might be more than two boundaries. at different points, and these points usually when we reach steady state, the values of the temperature will be fixed at the boundaries. Okay, when we reach steady state, the temperature of the temperature at these boundaries will be fixed, eitherwise at 2 sides or 4 sides. So this is graph represent the difference in the starting initial condition or auxiliary condition. You can see in initial condition we start from the same point, two functions, and here we start from two different points. We have y0 and we have y at L. This sort of problem, we call these boundary value problems. Okay, or B, shortly BVP. So let's take one example of these type of problems. We talk about heat balance across a rod. And what's given here, this is the equation or the heat balance for a long thin rod. And this is the equation of the heat, while H bar is the heat transfer coefficient. That's parameterize the rate of heat dissipation to surrounding air. And TA is the temperature for surrounding air. So TA usually is constant. What we want to compute, we need to compute the values of the temperature here. This is the unknown. Depend on the step size, how much point that we want to compute inside the rod. So this is will determine the size of the matrix that we want to build at the end. So to obtain a solution for this one, the best way is to use finite difference. So here to obtain the solution for this one, we need two boundary condition for the temperature at the ends of the bar. So the end of the bar, the temperature at the end of the bar should be known. We have temperature at xi. We have the temperature at x equal L. So by using this condition, we can solve the equation either by using analytical solution or by using numerical solution. So to solve this problem using numerical solution, we need to rewrite the derivative of the function. This is the second derivative here of the function by using central finite difference format, this one that we studied before in chapter 7. So here we can replace or substitute instead of the second derivative here by this format of the second derivative, and this is the approximation of the second derivative. While delta x square is the step size. So if you substitute in the equation like this one, substitute instead of the second derivative by the format from central divided difference by this equation here. After that, we multiply by delta x square, both sides, and we take the common factor or the input signal to the right hand, because this is constant, all these parameters are constant, TA is constant, delta x square is constant, h bar is constant. We take all these things to the right side, and what we have inside the rift is parameter, otherwise it is known from the information or it is boundary values or unknown. So let's take an example from the textbook. We have example 27.3. We have here a road with length 10 meters. If this is the length of the road is 10 meters like this one, And the step size is 2. So in this case, how many points that we need? So this is 0, 2 meters, 4 meters, 6 meters, 8 meters. Okay, so we have 0, 2 meters, 4 meters, because we increased 2 meters, so size 2, step size. So we have 2 meters, the first point. So the first point from the boundary far is 2 meters, and then 2 meters between the 2 points, so this 4 meters. And for 2 meters, so this 6 meters, 8 meters, and this is 10 meters. Okay, so we have here inside this one, we have 4 points that we want to compute. We have T1, T2 at 6 at 4, T3 at 6, T4 at 8 meters, and then 10 meters will be at the boundary, and this should be known. And given the information in the question, we have the temperature at T0. Here it is 40. This is the temperature at 0. And at the end here, 200. Okay, the value of h bar, it's equal 0.01. Delta x is 2 meters. So after that, we'll take alteration. Okay, we'll take alteration here. Okay, so if we take alteration, for example, for the first equation, if you talk about at node or T1 or at node number 1, here I is equal 1 because node 1, so I equal 1. If we substitute in the equation, in this equation, so instead of I, this will be 1. So here I have minus T0 plus 2 plus h, and h is equal 0.01 multiplied by delta x is 2 square, all multiplied by ti, and I equal 1, so this is t1 minus ti plus 1, so this is t2. This equal the right hand, we have 0.01 multiplied by 2 square. TA is given in the question is 20. Okay, so this value at the right is constant. T0 is given equal 40. So we have minus 40 here. So take it to the right hand side. Okay, and we multiply the parameter here inside this practice. That's multiplied by T1. And this will be, it's equal to 41 minus T2. This will equal 48. Okay, so this is the equation, the first equation. We have two unknowns in this equation, T1 and T2. Clear for the first node, يا شباب?
Yes, doctor.
Okay, so I will address this one if you don't have any question. Anything I need to repeat? I will type the other equation. After that, you complete this one. So at node 2 here, at node 2. So here I will be 2, so we have minus T1 plus what we have inside the brackets here is 0.01 multiplied by 4, all multiplied by T2. Okay, this is minus T3, and this equal 0.01 multiplied by 4 multiplied by 20. Okay, so this is the second equation for node 2. We substitute instead of I by 2, so here we have minus T1 plus 2 multiplied by 0.01 delta x square multiplied by T, because Ti, so this will be T2 minus Ti plus 1, so this will be T3, and this equal the value of the constant multiplied by Ta. So if here in this equation we have 3 unknowns, so the first one is minus Ta. The second coefficient now, we know this one is 2 plus h bar multiplied by delta x squared, it's equal to 0.04. This multiplied by T2, and this is the second term is minus T3. Okay, T4 is not appear now, and the value here is equal 0.08. This constant at this side. Okay, so we do the same for the third equation and the fourth equation. Because these values is unknown, so we put them in form of a matrix. After that, we just eliminate this one. Okay, after that, we just eliminate eliminate the, or use elimination method to find the value of this matrix. Okay, so this is the steps. Inshallah, I will update the handouts. I will submit it, inshallah, by today. Here, for the inner nodes, we have this for the first node, how we can compute this one, and we substitute by the values. After that, we finalize with this equation. Then for the second node at node 2, to find temperature T2, we have this equation. And you can see, Shabab, for each equation or for each node, if you want, when you talk about the road here, this is T1. If you want to find, this is unknown, we use T2 and T0. So this will be in terms of these two. Okay, so each one will be in terms of sub-round, because this temperature usually transfers in horizontally in the same mix. And this is for the third node. Okay, and this is for the fourth node, the equation for the third node. Okay, so after that, just we apply our skills to get a solution for this one. Okay, and yes.
يعني التغيير بس دائما بيكون في التي، ناخذ التي من خلال اللي هو الماتريكس اللي قبل شوي، صح؟
التي؟
ايه T1 T2.
Yes. هو depended on the node, how many nodes you have inside here, inside the road. Sometimes you have 3 by 3, sometimes you have 4 by 4. Okay. يعني number of the nodes that you have depended on delta x.
يعني الدكتور النواتج مالت الماتريكس هذه ما نستفيد منها، صح؟
كيف ما تستفيد؟ And you need to compute this one. This is the answer. This is your answer.
40 0.8 0.8.
Where's 0.8? This one?
الناتج حق الماتريكس هذه 40.8 0.8 0.8 و200.
كيف حتحل هذا بدون هذا؟
لا أنا في المعادلة اللي فوق ناخذ بس الأرقام اللي هي في البداية حق T1 T2، صح؟
This equation you talk about this one?
إيه أنا أتكلم عن هذه. الحين لما نعوض حنا هنا مثلا بصفر ولا 1 بناخذ قيم التي من الماتريكس اللي في البداية قبل اللي يساوي، صح؟
You talk about this one?
إيه. كلها دكتور معادلة كاملة هذه.
Yeah, the constant what you have inside this is the matrix, yeah. This is the equation. This is the unknown. The unknown you put it here. While the constant you put it on the right side. يعني مثلا في the first equation when we talk about node number 1 node 1 when we talk about node 1 الفيرست ترم صار عندنا t0 وفي النود 4 حيصير عندك 1. هذا في النود 4 لما تتكلم عن نود 4 حيصير هذا الترم عندك t5 and t5 is equal to 100. اوكي هذا t5 it is constant so no need to put constant here. الكونستانت حتحطها هنا حتشوف هذا 200 بلس البوينت 8. Khalifa, I answer your question or you ask something?
ايه اوكي دكتور الحين فهمت.
What we have in the matrix, we have 3 unknowns. Any term that's contained t1, t2, t3, t4. This is the unknown that we want. So this is the first column or the first column for t1, second column for t2, third column for t3, fourth column for t4. If you have values here, for example, this is plus 50, and here we have 1 or 10. So we take 50 here to the left side, because what we have to the left is the unknown with their coefficient. To the right will be the constant. Okay. Clear يا شباب? Any more question? Okay, so this is about the boundary problems, and here is a comparison of the exact solution with finite difference, finite divided difference method for different value of x. Okay, you can see how accurate this method. So the true, for example, when x equals 0, the true is 40, 40. That means we are at t0. We have x is equal to, and here we have 65, and here we have 65.95, and here and using the approximation we have 65.9698. Okay, so the error is very small when we have x equal 4. So the error also very, very small. Okay, so this is the end for this one. We finished the unit 9. Any question? Any question? So what we will study here, inshallah, in the unit 10 is again the solution for partial derivative. Okay, partial derivative problems, and again here we will use finite divided difference method to solve this partial derivative equation. It's similar to what we study in the boundary problems. It's similar, will be boundary problem style. Okay, so in partial differential equations here, this will be chapter 29 from the textbook, and also we'll talk about elliptic equations and parabolic equations, and how we solve them using finite divided difference, otherwise central divided difference or forward divided difference. So what we mean by partial derivative equation? So an equation that's include partial derivative of unknown function of two or more independent variables, we call these partial differential equation. So an equation include a partial derivative of unknowns of two or more independent variables, so we call this partial derivative equation. So for example, here we have the first equation contain the second derivative of u with respect to x plus 2xy, and then we have du square over dy. So here we talk about two independent. We have y, and here also we have x. So also the second derivative, we have the third derivative with respect to x squared, and also ty cubic or tu cubic over tx squared or dy. Okay, so here also we have the second order derivative of u with respect to y. So this type of question, we call them partial derivative. So how we solve them? Usually here we take an examples of heat transfer and Laplace or balance equations, Laplace equations to find the solution for this method. Again, here we'll study how we compute the temperature at the inner points of a grids. The classification of the PDF equations. Some classes of this equation are available, otherwise linear, second order, or nonlinear equations. Also, we can have three classes here: elliptic type, parabolic, and hyperbolic equations. So elliptic equations, one example of elliptic equation, we call this Laplace equations. And this type usually represents steady state response with two dimensions. Here, the present and or the derivative with respect to t does not appear in this type of equation, because here we talk about steady state when t goes to infinity. Parabolic equation, it's like heat conduction equation, time variable, one dimensions, and here it's contains second derivative and the first derivative. And the previous one in Laplace equation, we have second derivative t with respect to x, and the second derivative of t with respect to y. And again, we write this, or we rewrite this in terms of finite divided difference. The hyper methods or hyper equation, or we call this, an example of this is the wave equation. This is time variables with one dimensions. You can see here parabolic contain derivative with respect to t, hyper contain derivative with respect to t, while Laplace does not contain derivative with respect to t. Okay, and this wave equation contain the second derivative of y with respect to x over or equal 1 over c squared, and this is a constant multiplied by dy squared over dt squared. So how we can classify the equation if we have partial derivative, if two independent, how we can classify this equation? Eitherwise elliptic equation, or parabolic equation, or hyperbolic equation. So this is the standard form or the general form or standard form of the linear second order ODE equation, or partial derivative equation. With the constant here, if we have the second derivative du over dx squared, a multiplied by du square over dx square, second derivative of du over dx dy, plus c du square over dx square, plus d is constant, is equal 0. By knowing the value of these coefficients, a and b and c and d, we can classify the type of equation that we have. A and B and C are a function of x and y. D is a function of x and y and u and ux and u sub y. So by using the quadratic form, b squared minus 4ac, we compute the value of this one. If the value here is less than 0, so the type of the equation is elliptic equation. The second type of equation is parabolic equation. Here we have b squared minus 4ac is equal 0. The third type of equation, hyperbolic equation, we have b squared minus 4ac is greater than 0. So by knowing, if you know the general form, so this is the general form of the PDE equations. After that, you determine the values of a, b, c, d, which the coefficients of the parameters. If the value now is less than 0, so it is easy to. Okay, so if you look for Laplace, and the Laplace equation, we have dy square over ds square, du square over dy square, and this equals 0. So here, this is the coefficient is a equal 1 from this equation. P equals 0. P is the coefficient, dy square over dx dy. Okay, so this is equal 0. This term is not appear in the Laplace. C equal 1. Okay, d equals 0. If we substitute here, we have 0 minus 4, 1, and 1. And this is equal minus 4. And this will be elliptic type. Okay, so the Laplace form, Laplace equation is elliptic type. Okay, so any equation that's given, you can classify based on this quadratic form. So elliptic equation is an equation that's usually or commonly used to characterize the steady state systems and this indicated the present of the time derivative. So this elliptic equation, it's used to represent the behavior of the system at steady state. And we can identify this one. It is easy to identify by the absence of the time derivative. So this is usually used to determine the steady state distribution of unknown in 2 dimensions. A sample example that we'll study when we have a heated plate. So for this case, we have the boundaries or the boundaries condition of the plate are held at different temperature. So we talk about a plate like this one. The temperature at the boundaries here, for example, we might have a constant temperature at different sites. This temperature is fixed or held at different temperature because the heat transfer from a region of high temperature to low temperature. So we have a temperature transfer from the high region to the low region. So by knowing these boundaries, we can start computing the temperature inside the inner nodes or the distributed nodes inside this. We compute this using at steady state. So how we do this one? So the elliptic equation, we need to represent the elliptic equation unit using finite difference. After that, we will have a grade of the heated plate, represent a grade. And we distributed the grade based on the step size. We have step size in X and Y, and usually we assume delta X equal delta Y. This will simplify the solution. We can distribute the grades like this one. So we have delta X and delta Y. So the step size in X sometimes is different from the step size in Y, but here for simplification, we assume delta X equal delta Y and is equal H. So what we have inside, just the grades from square terms. After that, we want to compute the nodes, the temperature at these nodes. Okay, temperature at these nodes inside these grids. By knowing the boundaries, the value of the temperature at the boundaries, we have here different temperature. For example, here we have 100. Here, for example, we have 20. Here we have 50. And here, for example, we have 0 temperature. So by knowing these boundaries values or auxiliary condition, we can start from this one. After that, we can find the inner temperature or the temperature at the inner nodes. So for your heat conducting or conduction equation, is two type, eitherwise Laplace equation. Okay, so here when we have the function or the function f of x equals 0, or Motion equations here when f of x is appeared because f of x represent the source of the heat. So how we solve these Laplace equations? A Laplace equation appears in several engineering problems, such as studying steady state distribution of temperature in a body, studying the steady state distribution of electric charge in a body. So these things is represented by Laplace equation. So this is general form of Laplace. If we assume the source of the heat is 0 or goes to steady state, for example, if you have capacitance and this discharge at the end, discharge all the energy, so there is no condition inside this one or disappear. So in this case, we assume this 0. If the source of energy it appears still contains some energy or some heat, so we represent the value f of x. So when no heat source is available after we heat this one, so in this case f of xy is equal 0. Okay, so this term we equalize this to 0 and we can start the solution. So how we solve the problem here? Solution techniques. A grade is used to divide the region of interest. If you have any plate any plate that you have it, we divided this plate to a grid of nodes dependent on the step size that we have. So after that, we want to compute the temperature of unknown nodes. As we said, this is unknowns. We have temperature here is known because this at the boundaries, this will be known. Okay, and we want to compute the temperature at unknown nodes. To solve this one, as we said, here we'll use finite difference method by represent the second order derivative. So the first term of Laplace form is the second derivative, or t square over dx square. Represent this by central divided difference. And the second term also we represent this by central divided difference. To simplify, you can see here the step size is delta y and the step size here is delta x. To simplify the solution, we can assume delta x equal delta y and both equal h. So delta x here equal delta y and this equal h. So this will simplify the solution here. So after that, we can combine them. That means we can multiply both sides by h squared to eliminate these denominators from both equations. So this is the grid that we will use for the finite difference solution technique. So we can divide the plate to several grids. After that, we'll compute the temperature at the nodes step by step. Okay, so here, as we said, to simplify the solution here, we assume delta x equal delta y and this equal h. So that means if we multiply both sides by h squared, so this will cancel. After that, this term, with this term, we can combine them. Okay, so you will have minus 4tij, and this will be the equation of elliptic equation using finite divided difference. And now we can compute or write equation for each node. Because here we have the columns, I represent the columns, J represent the rows. So we can write the equation for any node. So for example, if you talk about node 1, 1, so we just substitute instead of I by 1 and instead of J by 1, and we write the equation. So depending how many equations that we have, that means if we distributed the nodes 10 by 10, so in this case we need 100 equations. If we increase the distribution, we might increase to 1000 equations. So this equation for small size or small grids is nice, but if we increase the number, this will be difficult. So at the end of this chapter, we can have another method to help us to find the solution. Okay, so this is the heated plate at the right. This is the figure, and we distributed this one to using the grids, and we have here some temperature, constant temperature at the boundaries. Temperature here is given. If this temperature, for example, 100, so all these nodes at the boundaries should be 100. Expect the corner. The corner is not defined. The angle here is not. We take this point from here to here, this 100. If you have here, this is 0, so all these nodes from here is 0. If this is 30, so all these nodes here will be 30. If this is 50, so all these nodes will be 50. Okay, so this is not defined the corner because here we have 50, we have 100. So also this will not include in the calculation, so I need to define this one. We don't have RQ here over this equation, this node. So for example, so this is the technique. If you want to find the temperature at this node, we'll use this equation. So you can see to find the temperature at node Ti or Tij. So we use the 4 nodes around this one. Okay, so we use here Ti plus 1j, Ti j minus 1, Ti j plus 1, Ti minus 1j. So this is both are center divided difference, because when you talk about this one, we take 1 point forward and 1 point backward. Finite divided difference. So this is central divided difference. We take 1 point forward and 1 point backward. And here also we take 1 point upward, and this is downward. So this is prediction and this is from the past. Okay, and both axes, y-axis and z-axis. So this will enhance the accuracy here. So this will be how we can compute the temperature here at this node. Easy method, yeah. So just we start this one, so it is easy. Let's, for example, take this, look for this graph. Look for this graph here, this grid. Given in this question, we have the temperature, boundary temperature here, we have here 50. So here we have at these boundaries we have 0, and here we have 50, here we have 100, and here we have 75. And now if you look for the nodes here, this nodes, this is column 0, so we have here T0, T0, 0, that means the first column 0, and this is the second, J is represent the rows, so row 0. After that, this node here, at this one, it's T01. Okay, and here we have temperature here at this node and temperature at this one. Okay, so also we have temperature here and we have temperature here at this node is given 100, and temperature at this node, and this here is also is given, this also is given, and this also is given. The temperature at this point also given, T0 or T10. This is column number 1, row number 0, column number 2, so T20 is 0 and T30 is 0. So after that, if you want to start with the first node, T11, column number 1, and here we have row number 1. Okay. So for this one, just we substitute here instead of j of I by 1 and j1. Okay, I1. So I1 here, I have 2, 1. So this will be the first term, T21 plus I1, J1. So 1 minus 1 will be 0. So I have T01. Okay, so that's contains 0. So this term, I will look for this one. This is given here. T01 is 27. Is given. So this is known. We substitute here. I have T1, 2, T10. Okay, T10 also is given. This one, T10, because when you talk about this one, you need this node and this node and this node and this node. This is the grades that we want to compute. And after that, this will be -4 T11. So this is the temperature that we want to compute in the first equation. That's multiplied by -4. And this equals 0. And because this is constant, we have here, this is T01 is 75. and here we have the second term here, T10 is 0. So we just substitute from the information that we have, and then we'll get the first equation for the first node. This is the first equation for the node 1, 1. After that, for example, we go for the second one, T1 1, 2 or 2, 1, J I equal 2, J equal 1. Okay, so we substitute in the equation. We just substitute in the equation here. So we have I equal 2, so this will be 3, 1. Here we have 1, 1. Here we have 2, 2. And this will be 2, 0. And here will be minus T2, 1. So this will be the equation. If some parameter is given, so we just substitute from the boundaries. So for this one, dependent on the grades that we have, how many points inside this grade, so this will determine the equation. Okay, so this is 9 points, so we need 9 equations. Okay, 9 equations. So in this case, you can see this will be 9 equation. We put them in this form. After that, we apply any methods, Gaussian methods, to eliminate this one. So during the exam time, usually we have less, like for example, otherwise 4x4. No need, for example, to have long term like this one ever. Or sometimes we just ask you to try the equation without solution, because the solution of these problems during the exam is too long. But we need to practice this one. This is very typical type of problems. Any question here, يا شباب? Any question here? Clear.
يس
موجود في الكلاس ولا خرجتوا؟
موجودين.
Okay. So this is another example. Also, some of these comes in previous exams, previous terms. So here it's required to determine the steady state temperature at all the points of a heat sheet, and the edge of the sheet are kept at a constant temperature, 150, 0, and 25. Okay, and this sheet divided to 5x5 grid. At the same method that we use, but here we take it step by step. Okay, so this is step by step here, like this one. So the temperature at these nodes is given 100, and the temperature at this boundary also 75, and the temperature at these nodes given. The temperature here is given. So what we want to compute the temperature for these or nodes inside. So again, we can start from T11 or any nodes here. We can start from. For example, here this is just explanation how we can do this one. For example, if you want to find the equation for T13, the first equation. So for this one, you can see this is the blue one are known for us because this boundary values, and these 3 red one to be determined. We need to determine these values. So we can write the equation of T13 by using this one, T14, 203, T12, and T23. So this is the equation. Some of the values are given, so we just substitute by the values and compute these and put them to the right side of the equation. Okay, so we can do it also for the other nodes step by step, and this also will be easy, inshallah, for you. Step by step, just you substitute by i's and j's. The first thing is you need to determine the boundaries correctly. Identify the rows and the columns. Okay, so this is 0 rows, this 0 column, j or I is 0, and this is j's. Okay, so this is the very important things. After that, for the equation, I think it is easy to get the matrix for this one. So at the end, if we get a matrix for this one, we just apply any methods for elimination to find the solution for this one. Okay, so you can see, Shabab, if we increase the number of the grades inside this one, so the solution of this system will becomes more complicated. So if you imagine, if you have 7 by 7, so that means you need 49 equation. If we have 10 by 10, so that means you need 100 equation. If it is 50 by 50, so you need 2500 equation to solve together. So this type of questions for small grades, this works well, I think, for a student, and it can be computed faster. But if we increase the number of the equation or the points inside the grade, so here will be more difficult. So to avoid this one, there are several methods are available. One of these methods is called Limpman methods, and this is one of the most numerical solution for Laplace equations. As we said, if we have, for example, 10 by 10 grades, we need 100 algebraic equation to solve. And in the previous method, you can see the maximum of 5 unknowns terms per equation. So if the size increase, so also the equation becomes more complicated, and this is need a lot of work, eitherwise by our hands or eitherwise by computers. One solution to solve the elliptic equations is, or the most common method, we call this Gaussian Seudel equation or Limpman method. So this is one of the easiest methods that can be used. So in this method, we just define the equation in this form. We have the same things that we need. If you remember, we apply finite divided difference. After that, we get a term that's multiplied by -4. This is the term is Tij multiplied by 4. So here we take this value of the point because this is the term that we want to compute, or the temperature at this node that we want to compute, and we divided the sum around nodes over 4. We take average of them. So by solving these alterations for I or j start from 0 to n, and also I from 1 to m, so we can use over relaxing method, and this we call this over relax algorithm. Use it to find the rate of converge by using this format. So how we can do this one? So we have a new value of Tij multiplied by lambda, a new Tij, this is the temperature for the node, the new value, plus 1 minus lambda multiplied by the old value of Tij. So while new Tij and old Tij are the values of temperature at the node Tij from the present and the previous alteration. While lambda is a weighting factor with the values between 1 and 2. The value of lambda is between 1 and 2. So when we stop usually when the approximation percentage relative error falls below a predefined value. So this is the method. For example, here use Lippmann methods or Gaussian method to solve the temperature for this grade. The same problem that we solved it before, but here we solved this by Gaussian or Gauss method with over relaxation with a value lambda is equal 1.5. Okay, and stop when approximation error is equal 1%. So in this method, يا شباب, by using this method, initially we assume all the temperature or the temperature at all the inner nodes are zeros. All Tij's are initially zeros. So we assume the temperature here is 0, 0, 0, 0, 0, 0. All these are zeros. We use only the boundaries for the auxiliary condition. So these at the beginning are zeros. So after that, we just compute the temperature for all the nodes. And then we update. Take alteration, alteration, alteration. So at the first node, Ti equal 1, J equal 1. So this is the first node. You can see if we substitute here and instead of I by 1, so this will be 2, 1. This is 2, 1. This should be 0. 2, 1 is 0. Here we have 0, 1. This term is 0, T01. T01 is not inner node. T01 is boundary. T01 is here. So this is not 0. It's 75. This one is 1, 2. This is 1, 2, 0. This one is 1, 0. 1, 0. This node. But this also boundary, but it is 0. Okay, so we just, and this is 2 or T10, but this is boundary value, but it is 0, so we substitute by 0. So now this is the value of T11. Okay, so now we use these values as a new value. This is the new value from the format. So this is the new value of T11, and the old value of T11 is 0. This is the old value here. The old value of T11 is 0. Okay, and this is the current value. So it is equal lambda multiplied by the new. It is 18.75 plus 1 minus lambda is 1.5 multiplied by T11, the old value. The old value is 0 because the initial value is 0. So the result will be 28.12. So we do it for all the nodes, the same things. We assume all the nodes are zeros initially. After that, we complete. We need to get a good start of or initial start of all the temperature of these nodes by using the boundaries. So as a result of this one, we complete computing all the nodes for all the nodes T33, T1, 2, 3, for all the nodes, we complete them. After that, we get all these, the temperature for all these nodes. So because we assume the temperature for all the inner nodes are zeros at the beginning, so the approximation error is 100% at the beginning. The second alteration, so this now becomes all this that we get now becomes the old values. And also this, it is used in this format now for the second iteration. Second iteration now T11, it's dependent on the previous value of T21 and the previous value of T12 Okay, and after that over 4, so will give us new values, and then we update. So we have new with the old, but the old is not 0 now. It's 28.12.5. So we do the alterations. Again, we update the window. Is the best way, ya shabab. You can type here, if you want to draw the window here. Again, you type the inner values, you update the grades. Or you can type here, for example, this old one. You use this old now to compute, because T11, again, you apply this form. After that, relaxation method, and you compute. We compute until we reach the error is 1%. So we'll take the second iteration and the third iteration until we reach the maximum error is 0.71. So now, if the error between the previous or the current and the previous estimation is 0.71, and this is the maximum error, so in this case, and it is falls below the stopping criteria, so in this case we can stop, and the final values of the temperature is given like this. And any questions, bro? Any question?